the other day. And as you know, we will just finish the book. Okay, let's see how far we can get. So the other day, I started talking about vorticity, and I said, okay, we will do something later on, and later on is today. Okay, so let me just remind what is the vorticity. So omega is the curve of V, and we're going to have this convention that in 2 dimensions omega is going to be a scalar, and in 3 dimensions it will be a vector. So then omega satisfies the following Euler or Navier-Stokes in 1D, sorry, in 2D or 3D. So dt omega plus v dot grad omega is nu plus omega into v. Dt omega plus v dot grad omega is equal to omega grad v plus nu plus omega. Okay, and okay, so the left-hand side is common independently of the dimension, and then there is this extra term in the case of 3D. Now that the pressure vanishes, because if I take the curl of the gradient, then I get rid of pressure. So typically, I'm going to refer to this term as the transport, and this term I'm going to call it the stretching or the vortex. The vortex stretching. So we can see now a big difference between what happens in 2D and between what happens in 3D. So in 2D, namely the vorticity is going to be transported by the velocity. Let's forget about the dissipation. So yeah, so we're going to have this scalar which is going to be transported by this velocity, and that's all that happens in 2D. Whereas in 3D, there is an additional amplification term. Okay, so omega can grow depending on how well it is aligned with grad v. Okay, so there is a chance. This is one big difference between why here there is global existence and here we don't know, because this may cause problems, and this is quadratic. So there is some chance that because if this were an omega, then we would have dt omega, quote unquote, omega squared. So that blows up defined time, right? So there is some chance for this system to blow up that happens in 3D and doesn't happen in 2D. Okay, so the vortex stretching can amplify omega when grad v and omega are parallel. Okay, so if these two vectors are parallel, remember that omega is a vector in 3D, then there may be a chance that it grows, and it grows in a quadratic way. So then there may be a chance to for a blow up to happen. Okay, so the proof of the equations is easy. I won't do it. Let's just take the curve in the Euler and Navier-Stokes equations and use some vector calculus identity. Okay, so this is a simple exercise, and I won't do it. Okay, so let me now say or state some consequences of this formulation. Okay, and for these consequences, I'm going to assume that there is no dissipation, so we are dealing with either the 2D Euler or the 3D Euler equation. So the first consequence is the following proposition. So suppose that I take my particle trajectories corresponding to the velocity v. The game I want to play here is before yesterday on Monday we were looking at the evolution of these trajectories and how the velocity may look like, or how the trajectories may look like as they move in time with the flow. So now what I want to look at is how the vorticity is going to change along these trajectories as I move time. Okay, so the solution to this equation is going to satisfy, and here I mean both, the following identity. So omega along the trajectories is going to be grad x along the trajectory times the initial vorticity. Okay, so this is my claim, and this is generic in 2D and 3D, and I will be more precise as to exactly what happens in 2D in a few minutes. Okay, so what I'm trying to see here is, and this will become obvious, that if I have a transport equation, then things are going to be nicely transported. I mean, the scalar here will move according to the velocity. Whereas in the other case, there may be some additional amplification coming from this part. Okay, so I'm going to prove that. And I'm going to prove it using a more general lemma. So let me take a velocity v of st. Nice. Not necessarily incompressible. With the associated particle mapping. So x satisfies what we would expect. So dx by dt moves along the velocity, moves along the trajectories according to the velocity v. Of course, x times 0 is wherever I put the map. Okay, so this is just simply the particle trajectory equation, the equation for the particle trajectory mapping, capital X according to the velocity v, which can be anything as long as I don't have any problems differentiating. Okay, so I'm not going to enter in this low regularity issues. Okay, so now let me take a vector field. Okay, so the claim now is the following. The PDE for H is the material derivative of H equals H plus grad V if and only if H along the trajectories moves according to whatever. So H satisfies this PDE in Eulerian coordinates if and only if it satisfies this evolution equation in Lagrangian. Okay, so this is the plan. Okay, now let's prove the lemma. In order to prove the lemma, this ones, this is a material derivative. So it's the time derivative plus the derivative vector by this velocity. So this is, I mean, this is related to a velocity. You give me a velocity, I give you a material derivative. And this makes sense because if I look at the evolution of my scalar or my function or whatever in Lagrangian, then if I take a time derivative here, then what am I going to get? I'm going to get the time derivative, but then I'm also going to get this evolution of x times the gradient of h. And this is exactly this. Okay, so it's the derivative in time along the trajectory. Okay. So far, all good? Okay, so let's take one derivative, or take a derivative alpha of 1. Yes. And this is something that we did the other way. So d by dt grad x is well, I apply the chain rule to this term. I differentiate in alpha and I get a grad b grad x. Grad b times grad x. I haven't done anything fancy here. I'm just taking derivatives and assuming that everything is nice and everything commutes. So I will not discuss any sort of like low regularity issues. Okay, so now I'm going to multiply this by h naught. We'll see in a minute why. Okay, so for now, bear with me. Now the point is that this is an equation for this function. Okay. Now I'm going to write an equation for this function, and I'm going to see that in fact the right hand side and the left hand side are going to satisfy the same case. Okay. So that's how this is going to work. So h of x equal to c satisfies, assuming this dt h equal to t h plus dtx h, and this is v, and this is the material derivative of h. This is h, v, at the bottom. And now we see this function and this function satisfying the same equation. Therefore, by uniqueness of ODE, they calculate. No. The X, H, right, same. One uniqueness. Okay, so this proves the lemma, which was more general, and that automatically satisfies. I mean, automatically proves the less general lemma simply by taking H to be on. Okay, so in particular, this implies omega. Now, let's try to analyze this equation better and see what is going to happen to the magnitude of the vorticity. Okay, not so much about how it moves or where it moves, but whether this vorticity may or may not grow, or what's going to happen. So remember, B is incompressible. Then the determinant of the Jacobian is equal to 1. Okay, so if we diagonalize this matrix and we look for the eigenvalues, then this is going to grow in magnitude as long as it is aligned with the eigenvector corresponding to the biggest eigenvalue in magnitude. Okay, so vorticity grows when omega naught, I mean, the product aligns with the eigenvector associated to the largest eigenvalue. Which modulus I mean, there are situations where, like if we had like a rotation or something like that, then everything would be of modulus 1. But generically, this happens. So if somehow we manage to make this omega naught parallel or as parallel as we can to the eigenvector of this matrix, then we are in good shape trying to produce a solution or trying to produce a candidate that may blow up. Okay, so this is going to lead to growth of omega, and of course this picture eventually gets destroyed, and this is why it is hard, because you can control this maybe for a short time, and you can sort of put the initial conditions in such a way that this is happening, but for longer times then it is difficult to control the evolution of everything. Okay, so that's difficult. I mean, of course, time 0 one can choose to make the vorticity to grow a lot, but one has to do this for the continuous period of time, and then the whole thing moves and the structure gets destroyed. Okay, so this is why it is conceivable yet difficult to fabricate some sort of scenario in that regard. And this would lead to finite time blow up again, because morally we can think of the equation dt omega equals omega squared. Okay.
Always because of the vorticity increases.
That's right.
I mean,
yes.
All the possible scenarios.
Well, this is an if and only if. So blow up, this is, if we have time, which I'm not sure, I wanted to show that blow up, if and only if the L infinity norm of the vorticity gets infinitely finite time, and the converse. So if the L infinity norm of the vorticity is controlled for all time, then no blow. Okay, so there is this analogy, and there is one can prove a theorem saying that it's an equivalent condition. So we'll see if we get that. And if we don't get there today, then we'll get there on Monday. So yeah, I may just by instinct, whenever I talk about blow up, I'm thinking about the vorticity getting being infinitely finite. But this is because this is already imprinted in my mind that if I'm looking for a blow up, then I'm really looking for a scenario where the vorticity okay, so now let's look at this. This is also a nice exercise in 2D. So in 2D, and understanding the 2D problem as a lift into like some plane of the 3D problem, then in 2D, then the matrix of the gradient of x looks like this. Okay, so if I'm sort of associating the 2D case as the planar case in 3D. Okay, so I'm lifting the 2D problem to 3D, but I'm considering that the velocity only lives in one plane. Exactly. So that then I would associate the velocity, the 2D velocity v1, v2 to the 3D velocity v1, v2, 0. Okay, and then I look at the 2D problem as a subset of the 3D problem, but all the velocities are only pointing in one plane. Okay, so if we do that, then the third coordinate of x doesn't move because we are on the third plane. I'm assuming here that we are on the x1, x2 plane. So then the gradient, so x3 is always going to be alpha 3, and therefore the gradient matrix is going to have this structure. Okay, and omega naught, and here I'm going to abuse notation a lot. This is okay. We can look at this as the 3D omega naught is going to be 0, 0, omega naught. Okay, so yeah, these are the same thing but different things. This is because of the abuse of notation coming from the fact that I'm taking the vorticity to the scalar and 3D vector. Now, what happens? So this times this is gone. Like this. If I just multiply omega on the trajectory, omega naught at the initial point. Okay, so vorticity in 2D is transported by the flow, no growth, just transfer. And we can also see that if we were to look at the equation. So if we ignore the Lagrangian point of view and let's forget about the dissipation, then vorticity gets transported by velocity, but there is no growth. Okay, so it just moves, but the magnitude of the vorticity doesn't change. Okay, so this is vorticity. Okay. We can see from these 2 points of view, 2 sides of how to look at the equation, Lagrangian and Eulerian, that exactly this happens. So if we were to start with a block of vorticity, then the block will move here and there, but it's not going to dramatically increase or something like that. And this also goes along the lines that for 2D there is no blow up. because the verticity is going to depend on. Okay. Further to analyze, that not just the L infinity norm is conserved. I mean, well, no, from this, it is trivial to see that the L infinity norm of omega is conserved. But, for example, it's also not too hard to see from here that since V is divergence free, the LP norms are also conserved, forgetting about the dissipation. Okay, so we multiply by the right power of omega, integrate by parts. This comes into V as a divergence, and this is gone. And as I said, let's assume that our data is smooth and I don't have any problem integrating my parts. So, follows my parts plus the incompressibility. And Claudia may talk in more detail about what other properties or what other things can happen in whenever the setting is not so nice, not so smooth, and one cannot integrate by parts sort of without thinking too much. Okay. Good. Up to here. But let's see. Okay, so other conserved quantities which say in 3D that I'm going to mention, and I won't do the proof because most of these proofs are very similar to each other. So I will just can you deduce LP norm conservation from the PDE satisfied by omega directly? Yes. Without using that the divergence is 0? No, you need to use that the divergence is 0. And is it implicit the incompressibility in the PDE for omega? No, I didn't write it, but yeah, it should be coupled with the divergence of V is equal to 0. So you really need the incompressibility. Okay, so something that is conserved, for example, is the velocity flux. Integral of V, or integrals here in the vorticity flux. The integral of omega is also conserved. The kinetic energy, this is important. Velocity. Equals I don't know how to do the cross product. This is the cross product between x and omega. And the moment of fluid impulse. So we're going to do C. and the rest are mutatis mutandis, it's very similar. So I'm going to do conservation of the energy. Now, these things are important, I mean, in many ways, because if you have a conservation law, this this can help you towards proving local and global existence, or in maybe some different contexts. I mean, the system is Hamiltonian, so there may be other like first integrals and quantities that are conserved. So looking at the Euler equation from a more of a Hamiltonian dynamics point of view may also be helpful. And then the conserved quantities play a central role in that point of view and in that set. Okay, so this is in R3. There are analogs in R2. But I'm not going to write here. But you can imagine that the proofs are like pretty much the same. So let me try to prove the kinetic energy, which is not too hard. So I'm going to use the following lemma. So suppose that I have a smooth function, divergence free, maybe omega. Okay. Okay. And B, another smooth. Okay, this is a smooth scalar. So I can control A and B at infinity by this decay rate. Okay, and this always a little. Okay, so assume that they have nice functions that at infinity decay nicely. Okay, then so this is then the integral A grad B is C. Okay. So let's prove it. I mean, this is a simple calculation, but this is going to help us to infer the conservation laws for, let's say, for the energy. And of course, the energy here, I'm not assuming any other like forces like gravity or anything like that. This is just simply like the kinetic energy. So let's prove the lemma, and this is the all proof. I look at this integral on a big ball, and I use Green's formula. I integrate by parts, and here's where the divergence free will come to help me. So the Green's formula is the divergence rate is 0. The integral on this ball simply the integral. Now, if I move the gradient onto A, this is gone, and I'm only left with the boundary there. Okay, so okay, and now I use the decay. So now since I can bound this whole thing, so now since A, B, N is the low, okay, the 1 minus N, and the measure of the integration region is some number then N minus 1, then this whole integral goes to 0. So now, armed with this lemma, the plan is to look at the derivative of the kinetic energy and write it as something of that sort. And this is literally what is going to happen. So now proof energy conservation. So now I'm going to use the transport formula that we discussed the other day. D by dt. I'm just writing it up, and I'm going to use it with the whole space. So d by dt integral x omega t f integral okay. So this is the formula that we discussed the other day. I take x of omega t to be everything, and f to be 1/2 modulus of b squared. Substitute by the derivative, and then d by dt using the equation. So this is the derivative of the energy is given by minus the integral of b dot graph t. And now I use that in the space of functions that I was considering, everything has the right decay, everything has a good enough decay to conclude that this is it. Okay, so I wasn't precise at all as to what were the exact assumptions that I was taking whenever considering growth or decay at infinity, and I will still sort of keep doing like that. Okay, I won't be very precise when it comes to what is the right smoothness and what is the actual amount of regularity that I have to assume. Okay, so I want to keep it more or less clean. I want to sort of get into like the critical space or you know the right space and so on. After all, this is an introductory course. So good. Now let's talk about something else, which is in principle not connected, but we will see that it is connected to vorticity. Okay, and for now it will look very different, but later we will see a connection, and even later we will see a much bigger connection. Okay, so if we recall Euler in velocity form, so we have dv dt minus grad t plus nu Laplace v, divergence v equal to 0. So, I mean, if we look at this, sure, there are 4 or n+1 variables, n+1 equations, and n+1 variables, n coming from b and 1 coming from p. But there is no evolution for p. So this looks odd, like, okay, sure, there is a p and p is determined by this, but how can I say something about p as time evolves? So there is no evolution equation for p. Okay, so what can I say about p? Let's say not at time 0, but at time 1. Okay, how could I tell what is the right p? What is the p that kind of satisfies this equation? And this is a little odd because I don't really know how the p is going to evolve through some derivative or through some operator, but it's just more in an implicit way given by the evolution of v. Okay, so let me rephrase this question. So this principle may look dangerous, but let's take the easy way. So can I get rid of the pressure? Okay, so can I find a simplification of the equation and get rid of the pressure? Okay? And of course, I will pay a price, and the price that I will pay is I will pay getting rid of one variable. The short answer is yes. So I will pay getting rid of one variable by paying with one equation. And the equation that is more likely to be used to pay that is the last one, right? I mean, it would be odd if I paid with the evolution equation of one component and yet kept the other one. So the natural thing is to trade this variable for this equation. Okay, and this is actually what we're going to do. So if I were to reformulate this question, then let me rephrase it slightly differently, but sort of meaning the same. So can I find a given P of V? So for every V, can I find a P in such a way that this whole thing closes? Okay, so as I said, the short answer is yes. And we'll figure out how to do it. Okay, so something that is going to work for our advantage is the fact that we know that the divergence of V is 0. Now, if we were, like, if you remember how we got the evolution equation for omega, just took the curl here, and then magically this disappeared, and there were some omegas sort of happening here and there. Now let's try to see if by taking the diff of the top equation and using the fact that dv is 0, we can simplify things. So if I develop the material derivative, okay, this is, I'm not doing anything, I haven't done anything now, I take the divergence here. So divergence of V is 0 for every t, therefore divergence of Vt is 0. Good. Similarly, the divergence and the Laplacian also commute. Okay, so far we're doing fantastic. Now, divergence of the gradient is equal to the Laplacian. Okay, not bad. And okay, and this is amazing. So okay, so after doing this, no evolution, which is good, and we have found a compatibility condition for P in terms of V for any time. So we have, I mean, we can write this a little better. So the divergence of V grad V is equal to the trace of grad V squared, which PR, Vj, Vj, VR. Okay. So now, what do we have? We have essentially, okay, some right-hand side, well, this is the left-hand side, but I usually put the Laplacian on the left. So we have a Laplacian of something equals some right-hand side, but at this point, I don't care too much. So pretty much, we have an elliptic equation for P. Okay, so if I didn't like the P appearing in the PDE, then there is a way to get rid of the P and write the whole system in terms of P. Okay, so essentially I can solve this. Laplace P equals something, so P becomes the integral of n times the trace grad V squared y t d t. And here n is the Newtonian potential, depending on whether we are in dimension 2 or dimension n. So it's either a load or a power. So Newtonian potential. X multiply log x, 2, and then some constant x 2 minus n. Okay, so that gives us p as a function of v, and now there is no p anymore. I mean, we can also write, this is the expression for p, we can take the gradient and differentiate under the integral. Again, I'm assuming anything I need in terms of smoothness, so that p is Cn integral x minus y to the power n, the trace of that p over p, well, p. Okay, so now we can simply substitute back into this equation, and get a closed system for V. So dV dt minus Cn this term. As I said, this is now a closed evolution equation. Okay. Now, I mean, now this is too good, right? Because we have 4 equations and 3 unknowns. So now what I'm going to prove is that in that setting, the divergence of V is equal to 0 is superfluous. We can remove it. So now, of course, assuming that the initial data is divergence free. So now we want to see that if divergence free times 0, then it is divergence free that's the plan, and this is not too hard. So what I'm going to look at is the evolution of the divergence of V. Okay, so I want to take actually divergences here, here, or here, here, and then see what sort of PDE does diff V satisfy. So if I take, okay, let's look at the equation and the evolution equation for divergence of V. Then it's not difficult to see that we have the material derivative of divergence of V is equal to nu plus divergence of V. Okay, so that looks good. I mean, this is strongly suggesting that if I start with divergence of V naught equal to 0, then I'm going to keep being 0 forever, because this will help and this structure is going to be preserved. So now let's prove it using energy. So we go. I want to essentially what I'm looking here to prove is to prove uniqueness of solutions to this equation, or at least uniqueness of the zero solution to this equation. The solution that is zero at the initial time t is equal to 6. If I do so, then I win. Okay, so we now do energy estimate, and now let's argue by contradiction. So assume that we have U1 and U2. U is the divergence of V, such that V Tuj plus V grad Vj is equal to nu delta Uj. Okay, pretend that the U's are the divergence of V. So now I'm going to look at the evolution of the L2 norm. So dt half U1 U2 square is 1. So if I take the derivative and I put everything together, then this is equal to -1/2 the integral of V gradient U1 minus U2 square plus the dissipation. 1 2 delta U1. Okay, so this looks already pretty good because again, you can integrate by parts. You can move the gradient onto V. And here we move the delta, or one derivative of the delta, onto the other side. Okay, so now this is great. This has a good sign, so I can throw it away. I mean, I could even take advantage of this, but let me just even throw it away. So this is bounded by 1/2. Now, for now, pretend that the divergence of V is bounded, which I can always assume this at least for sufficiently small time. So because the initial data was nice and the divergence was bounded, then this is going to hold for a short time. So there is a constant times the integral of U1 minus U2 square. Okay, so that already gives me unique or local uniqueness in time. Okay, so as I said, so here I'm assuming the bound divergence of V, that's an absolute constant, which is okay for at least. Okay, so in particular, this implies uniqueness for equation 5, which was okay. So what does that mean? Again, if the divergence of V at time equal to 0 is 0, then the divergence of V is going to be 0. Okay. So yeah, just to maybe give a different point of view of what we have done here. Okay, when we got rid of the pressure and when we sort of try to get a closed system for V, I mean, this looks sort of like magic, but because we can solve for the pressure and life is good. But if we were to think about what we are actually doing here, we are projecting the equation and everything onto the space of divergence-free vector fields, and then looking at the projection of the equation in that space. Okay, so another point of view what we're doing is to project Euler or Navier-Stokes onto the space of divergence free vector fields. Okay, so what do I mean? So I'm going to be slightly more specific here, because sometimes this leads to nice calculations, or if one tries to do numerics and tries to implement these equations using maybe spectral methods, then this comes in helpful. So what I mean here is the following. If okay, so if I define P, this is called the Leray projector of V is equal to W, then the divergence of W is equal to C. P of V is equal to V if and only if the divergence of V is equal to C. Okay? So this is the sort of operator that I'm applying onto the equation. And now if I were to look at this in this abstract setting and I hit the equation with the P, then what do I get? Remember, P of V is equal to V because we are in the setting where the divergence of V is equal to 0. So what do I get? I get V T. This is fine. This doesn't change. Yeah. What do you mean? Yeah, it has to be the orthogonal projection onto this space. It has to be like the orthogonal projection onto this space. Yeah, sure. So let me finish, and I will be more specific as to how to define the P. Yeah, this is informal in some sense. So if I hit it with the P, then this is sort of what I get by removing the P of B. So if I were to write the operator P in Fourier variables, so in Fourier, which is kind of the interesting way to look at this from the point of view of doing numerics. Then what I'm doing is P of U is equal, so P of U is U minus this operator P. Okay, so the gradient of the Laplacian inverse of the divergence of P. Okay, and if I were to write this in Fourier as a multiplier, then P of U of C is some multiplier, which is a matrix, times U hat of C, where the matrix is given by delta Kj minus Cj Ck over C squared. Okay, so this is a better definition as to what do I mean by the operator P. And here you can see that this is literally this. Okay, so this may play a role later when we talk about singular integrals, but for now, let's leave it like that. I assume everyone understands the notation and everything. Okay. So now, let me also present another way to look at this problem. Let's say for now in 2D. Okay, so I'm going to talk about the vorticity stream formulation. Yes. Sure. Why is the pressure not in the equation? Because the projection of the pressure term is going to be 0. That's what we wanted to do. Okay, so yeah, for now, let me assume that I'm 2D. Okay, so I'm going to use a little bit of the structure of being in 2 dimensions. Okay, so the first thing that I'm going to use is that if my V is divergence free, then I can find a C, which is okay, up to a constant, which is called the stream function. But I can write the V as minus V2C, V1C. Okay, and here is probably when I'm going to make a lot of mistakes with the signs, because the definition of this operator depends on the person that you ask, and then there are. This is a very easy source of sign mistakes. Okay, so I hope I don't make too many, but in case, be aware. Okay, so okay, so far it doesn't look as if this is too helpful. Let's see what is the equation that C satisfies. Okay, so let's take the curl of this equation. Okay, I want to relate the stream function with the verticity. Okay, so if I take the curl, then on the left, I get omega, and on the right, I get the Laplacian of C. Okay, so now I have a nice formula for C in terms of omega, and this in turn is going to give me a nice formula for V in terms of omega whenever I hit it with a perpendicular gradient. So now I invert this equation. C into V, this is the convolution with the log. And if I take perpendicular gradients, then V is 1 over 2 pi, the input C is going to be something that I'm going to write some kernel K2 on board with omega. Okay, and here K2 is a homogeneous kernel given by minus x2 mod of x squared, x1 mod. Okay, so now this is a singular integral, and this equation is usually known as the Navier-Stokes law. So this is what people refer to when they talk about the Navier-Stokes law in the context of fluid. Okay, so this is. So what have we just done? So we have found a relation between V and omega in a way that we can, if we were to write our system as a closed equation for V, now we can write the system as a closed equation for omega, which was not immediately clear when we wrote down the equation for omega, because in in the derivative in transport terms, there was a b. So it was not so clear that we could invert the curve operator. Okay? So we have found a closed system here. So d omega dt equals nu plus omega 0 times 0, and b given by this term K2. And the pressure, if we were to go back to the original formulation, is Pi dj, Pj, Pi, and so on. Okay, so my point is that this is a self-contained equation now written in terms of only omega. And from here, we know everything from the original equation. Okay, so I did the derivation in 2D, but in 3D one can obtain more complicated, but in similar spirit, similar formulas. Okay. So that's good, because this sort of allows us to look at whichever equation is more favorable to us, either the velocity or either the vorticity. Okay, so we have seen that there is an equivalence between one type of equation or one equation and the other equation. Let me also mention something in preparation for the future. This is also related to what Jamin will talk about. So if okay, so set nu to be 0. I'm now going to talk about the Euler. And now if we write this equation in terms C, so now I'm going to substitute here in the material derivative as much as I can the omegas and the b's in terms of the stream function. So what am I going to get? I'm going to get that omega t plus d1c d2 delta c minus d2 c d1 delta c is 0. Again, I'm taking nu to be 0. Okay, so if we look at this, this is kind of like a Brownian or kind of like a determinant of something. So if C and delta C are functionally dependent, so in other words, if delta C is some function, capital F of C, then this term vanish. Okay, so that solution, C and the associated B, omega, and so on, will be a stationary solution of Euler. Now, what's the advantage? If instead of this now, which doesn't look too good, we look at this, this has a better chance to work or to be amenable to techniques, particularly coming from elliptic theory. Okay, so if we were to look for solutions of the 2D stationary Euler equation, then this sort of equation, okay, depending on F, looks much more amenable. So this is the advantage. much more amenable, let's say a priori, to techniques coming from elliptic PDE. And here I'm particularly thinking about the maximum principles moving planes and so on. Okay, so I don't want to step too much into Jamil's lecture, but he's going to talk a lot about this, and he will especially talk about the situations where this can be done. Okay, so this is more classical, and then we'll talk about other situations where this is not true or not possible, depending on it. Okay, so let me state, and I won't do the proof because so I will leave it as a cliffhanger for next week. So now I want to talk about the connection. This is also related to the question at the beginning of the class. So between global solutions, finite time singularities, and vorticity. So if we now consider and 3D Euler, so let's drop the viscosity. Then the main goal of what I want to talk about is the following theorem. So this is a theorem which is by now classical, proved by Biel, Kato, and Mayra in 1984, which essentially says, so I'm going to state it today in an informal way, and I will be more precise later on. Essentially says that blow up or not blow up for Euler, if and only if the integral in time, or time t, of the L infinity norm of the vorticity bounded. Maybe I should try this like this. Okay, so this is an equivalent. So if we control this object, then we win, or I mean, then there is no blow up. So this is something particularly useful because now we can study the evolution of omega, and in particular for free, it will give us the global existence in 2D. Okay, so that's the plan for next week. I won't do it in 4 minutes. And there will be something like I promise. Okay, so let's leave it here and we'll continue next week. Any questions, comments on the chat? Juan Carlos? This is clapping. I thought it was a question. Okay. No, if not, okay, good. So if not, we'll see each other next week. Okay. See you.